for the opportunity to speak about my work to your group. So yeah, today I'm gonna tell you a story, the story of the journey of the inverse approximation. And then during the second part, I will talk about this fantastic project called SkyPy. And so before going into any details, let me say a little bit briefly something about myself. So as you already mentioned, I come from a very theoretical background. So I've done quantum cosmology, I've worked on effective field theory of dark energy, and during my PhD, I worked on effective field theory of large-scale structures, redshift space distortions, and halo bias. And then after 1 year teaching, I am now a postdoc at the University of Manchester, working with Sarah Bridle. I am a member of DES, one of the co-founders of the SkyPy project that you will learn about today. And currently I'm working more on the observational side, so working on weak lensing and unequal time correlators, and I am also applying for jobs. Right, so enough about myself. Let's start with the first part. So this is the journey of the inverse approximation. And this is going to be a series of 2 papers coming out very soon, hopefully next week. So yeah, during this part of the talk, I'm going to walk you through different things. So we're going to start with a very simple introduction to cosmic lensing. Then I'll tell you the story of the inverse approximation, and then I'll focus on the 2 key components of my project, which is the all angular approach and also the unequal time correlators. And then I'll give you some results, some preliminary results and a summary. Right, so let's start. Cosmic lensing. So imagine that you are looking at the sky and you observe different points in the sky, and you know that each of them corresponds to a different cosmological distance or redshift or time. So we have in mind this onion-like kind of picture of the universe. And cosmologists usually, to explore this large-scale structure of the universe and this picture, we usually compute correlation functions, correlation between different fields in the space. And just a little bit of notation here. So if you compute or measure the correlation at the same time slice, then you talk about equal time correlators. But when you measure the correlation at different time slices, then you talk about unequal time correlators. And some examples of fields that are involved in cosmic lensing and weak lensing in general is the density, matter density fields, and convergence, which more or less tells you about the magnification of the lensing effect, and the cosmic shear, which tells you about the distortion that this lens generates. So the idea is, because we observe within the past light cone, we need to perform projections of the fields in the 2-dimensional patch of the sky. And by doing so, we can compute, for example, the angular correlation function, omega of theta, where theta is the angular separation on this 2-dimensional patch of the sky. And this quantity involves integrals over the 3rd direction, the co-moving distance. And then we find here some filters that depend on the galaxy survey, the selection function of the galaxy survey that you're working with, and also the unequal time correlation function, which measures the correlation between density fields, matter density fields at different time slices. Right. You now can perform some expansion in terms of spherical harmonics and work in Fourier space and compute the angular power spectrum, the CLs. And this involves an extra integral over the K range. And the new bits here are these spherical Bessel functions and also the unequal time matter power spectrum, which is simply the Fourier transform of the unequal time correlation function. Right, so you are all set, and now just you need to compute these integrals, right? But some warning here, these are really hard to compute, okay? And the angular power spectrum is even harder to compute because these spherical Bessel functions are really, really highly oscillating. And also because this unequal time matter power spectrum is not being very well understood in the literature. So this is basically the motivation of my work here, solving these integrals. Now I'm going to tell you the story, and I'm going to tell you what's the journey of the inverse approximation, how did people in the past try to compute these integrals, and how people in the present are doing this. Right. So before doing so, to solve these equations or to solve these integrals, you can play around, for example, with filters. You can play around with the spherical Bessel functions or make some assumptions on the unequal time correlators. Limber was the first one in solving these integrals. In concrete, he solved the angular correlation function, omega of theta. And for that, he made different assumptions on the filters and also the correlation function. So he assumed that the filters were smooth enough and that the correlation function falls off fast enough so that instead of looking at the two different redshifts, he could evaluate all these quantities at a mean redshift, okay? So he ended up with a much simpler expression. And also, typically, when one uses the inverse approximation, also applies the small angle separation approach, right? So for small angle separations. So that's Limber. And then 20 years later, Peebles, he applied this approximation to the spherical case and also for this Crete galaxy survey. And then in the late 90s, Kaiser, he re-derived this expression for the flat sky approximation and for a curved universe using some Dirac deltas along the way, also getting a much simpler expression. But all these things are approximations, right? And Patrick Simon, in 2007, he published this amazing paper where he addressed the issue of the accuracy of the inverse approximation. And basically, he concluded that you can use Limber for small angle separations, but if you want to look into larger angle separations, you're better off using something else. For example, what he proposes, the thin layer approximation. More interestingly, Simon compared the inverse approximation versus the exact calculation. However, this point was not very clear to me because for the exact calculation, he also applies the small angle approach. So it's actually not that exact. Bottom line from Simon, Limber is not accurate. Right. I've told you that you can also play around with these spherical Bessel functions that are, this is the difficult part, right? Because it's really highly oscillatory. And typically, you can approximate the spherical Bessel functions to the amplitude of their first peak using Dirac deltas. And this is what I call the Dirac delta version of the inverse approximation. But this is only valid for very large, for large values of L, right? So for small angle separations. And people have put effort trying to extend this approximation, performing different expansions. And this is what we call the post-inverse approach. For example, this paper by Loverde et al. In 2008. But it's not clear yet how they deal with the divergence on small values of L. All right, 3 years ago, Lemos et al., they also published this very nice paper where they not only apply the Dirac delta approximation to the Bessel functions, but also use the geometric approximation to the unequal time matter power spectrum. The geometric approximation is simply this idea that instead of having the full correlation along the line of sight from one redshift to another, simply compute the power spectrum at one redshift and the power spectrum at another redshift. And that's the geometric approximation. And it's only very good on large scales. Then you end up with a much simpler form, but this is only valid for large values of L and small values of K. Right, Last year, Fang et al., a very nice paper as well, using some FFT log methods. The key point for this paper is that they not only play around with all these factors here, but also pay attention to all the scales of the universe, right? So they take this integral and they split the integral into two parts. So the linear contribution and the non-linear contribution. And for the linear contribution, they are able to compute that exactly by shuffling around the order of the integrals. But for the non-linear contribution, they claim that they don't have to compute the unequal time power spectrum because they apply the Dirac delta approximation and also the geometric approximation. However, this is not clear to me, or it wasn't clear to me, because the geometric approximation is good on very large scales. And the nonlinear regime is for increasingly smaller scales. So it wasn't clear to me how they dealt with the nonlinear physics. And after reading all this literature, I came up with this list of issues that are still open. So these issues are regarding the accuracy of the Limbus approximation, the divergence on large angle separations, the goodness of the geometric approximation, and the accuracy of the nonlinear physics. So it was very clear to me that we needed to compute the unequal time matter power spectrum and also compute these integrals at all angular scales. And that's my work. Right. So now I'm going to explain the two key components of this project, and I'm going to start with the all angular approach. And for that, I'm going to tell you how I came up with this project. So basically, I was looking at these integrals, and I really wanted to know how to compute these. So my idea was I knew how to compute the unequal time matter power spectrum, and I wanted to deal with nonlinear physics. I wanted to include one loop expansions and also effective field theory. And I wanted to see what was the impact on weak lensing. I didn't know how to integrate this. So I also came up with another approximation, which is a midpoint approximation. And I wanted to compare this with a geometric approximation. And this is going to be available as a Python package called unequal pi. But then again, I really wanted to compute these integrals. So Nicolas, Tesori, and myself started working on the numerical methods, and we came up with a method that provides you with the exact calculation at all angular scales. We use some FFT log methods, but the key point here for this approach is that instead of computing the angular power spectrum, the CLs, basically, take your matter power spectrum, inverse Fourier it, transform it, and get the the correlation function in real space. Then compute the angular correlation function and transform it back again to obtain the CLs. And this is much better. So after doing this, we analyzed the regimes of validities of all these approximations that I just mentioned. And also perhaps I'm going to convince you and convince myself that we can drop any kind of approximation at the end of these calculations. Right. Let me focus today on the unequal time power spectrum. So as I explained earlier, cosmologists usually compute two-point functions. And for that, we rely on a universe which is homogeneous and isotropic. So if you want to define what the equal time power spectrum means, this is the correlation at the same time slice. This is simply this equation over here. It's simply the correlation between two, in this case, matter density fields at different scales, K1 and K2, but at the same redshift, Z and Z. But it is really straightforward to compute the unequal time power spectrum, which measures the correlation between two different redshifts. And it's simply, instead of having the same redshift, you evaluate these two fields at different redshifts, Z1 and Z2. Right, so I'm not going to overwhelm you with all the huge equations. So to give you a hint of how this works, at the level of linear theory, the traditional equal time matter power spectrum, P of K and Z, you know, it's simply the square of a growth function times the linear power spectrum at redshift today, for example. Right. And the unequal time power spectrum is basically the product of the growth functions at these two different redshifts, Z1 and Z2, times the linear contribution of a power spectrum. And as you can imagine, if you set Z1 and Z2 to be the same, you'd retrieve the equal time prediction. Right, but I told you that I wanted to compute these things because I wanted to deal with nonlinear physics. And for that, I had to go to higher order corrections. So I went to one loop theory. One loop theory is simply these three terms over here. So the linear contribution P11 plus the loop corrections P22 and P13. I computed these using standard perturbation theory, but my expertise is on effective field theory of large scale structure. And I knew that at the level of the equal time power spectrum, EFT is much better at encoding all the nonlinear physics than standard perturbation theory. And for those of you who are not familiar with the effective field theory formalism, I'm going to tell you a very brief story about this. So basically, I always like to explain EFT with hot chocolate. So imagine that you have your hot chocolate and that you want to measure the density of your hot chocolate, which is a macroscopic quantity. You know that your hot chocolate is made of hot chocolate particles, and all these particles are constantly interacting with each other through collisions, and you know your hot chocolate is viscous, so there is viscosity terms and all these kind of things. And this microscopic physics is affecting your macroscopic measurement of the density. The thing is, standard perturbation theory is not able to account for all these messy nonlinear physics, but EFT encodes all this information into one single free-fitting parameter, which is the counter terms. So basically, EFT is standard perturbation theory plus this counter term that takes into account all these microscopic physics. So I computed all these things, but unfortunately, it seems that the unequal time effective field theory seems to break, is not the perfect prescription for the unequal time correlators. So that's why I came up with this new idea of the midpoint approximation that we're going to learn about this in a minute. Right, so we have all these grid of theories. We have standard perturbation theory, we have effective field theory, and for those we can compute the geometric approximation. Remember, the geometric approximation is only the power spectrum at one redshift times the power spectrum at another redshift, and we can compute also the unequal time power spectrum. In this diagram, if you compare columns, you are looking into time effects. And if you compare rows, you are looking into nonlinear effects. I'm going to focus only on the time effects. So I'm going to compare only columns. And this plot shows you the error that you make when you use the geometric approximation instead of the full information from the unequal time matter power spectrum for both, for standard perturbation theory and for the effective field theory framework. Right, this is done for a mean redshift 0.5, and then I change the redshift separation. Right, so the red lines corresponds to effective field theory, and the black lines corresponds to standard perturbation theory. Right, so we can see that for increasingly larger redshift separations, the error is much larger for both frameworks. But the key aspect here is that it seems that effective field theory breaks at some lower K value than standard perturbation theory, and also it tends to have a much higher error. So which one is best? Truth be told, this is not a trivial question to answer. There is not a trivial answer to this question, right? So the only thing I can tell you is that effective field theory breaks when standard perturbation theory does not. So yeah, the idea is how we compare this with the real universe. We don't know. Maybe we need some data, or maybe we will need some simulations that can give you all these full and continuous information from one redshift to another. But this is not possible nowadays, right? Because simulations, they have these step size integration methods that only provides you with snapshots at different times. So it's not a really easy answer. And that's why I pick the standard perturbation theory for my analysis. And also, that's why I came up with the midpoint approximation. So this plot is very similar to the first one. And I'm looking at the error that you make when you use either the geometric approximation or the midpoint approximation instead of the unequal time power spectrum. Midpoint approximation is the black lines, and the geometric approximation is again the red lines. We can see that these approximations are more accurate for small redshift separations when you retrieve the equal time prediction. And if we focus on the geometric approximation, we see that it's really good on very large scales. We already knew that. But the error increases monotonically on increasingly smaller scales. Whereas the midpoint approximation, even though it's not perfect on very large scales, the error seems to be much more flat, much more stable, and it seems that it might give you a much better prediction around mild nonlinear scales, because we have this flipping sign effect where actually the midpoint approximation equals the prediction for the unequal time matter power spectrum. Right, so what's the impact of this on weak lensing? Let's see. So the preliminary results I'm going to show you for this, I have computed all these 4 approaches. So I have computed the exact calculation using the unequal time matter power spectrum and using our new method called Corfu. I have computed the Limbers approximation, the geometric approximation, but remember here, the geometric and the Limbers approximation is not the same, even though some authors, they use it combined. But remember that if you use the Limbers approximation, you actually do not have, or you don't have to compute the geometric approximation. And it's different because the first one, the Limbers, it only gives you one integral, whereas the geometric approximation, you still have the 3 integrals over here, right? And then the midpoint approximation, where instead of the full and equal time information, you just take the power spectrum at the mean redshift. Right, so let's see. This is the results for this year 1 data. I have computed here the angular power spectrum for convergence, galaxy clustering, and galaxy-galaxy lensing. And what you see here is the ratio between the CLs from one of these approximations, Limbers, geometric, or the midpoint, when you compare that with the prediction using the unequal time correlators. So the closer to 1 in these pictures, the better your results. And it's really astonishingly that, or surprisingly, the fact that the geometric approximation and the midpoint approximation seem to mimic very well all the unequal time features, and all the difference that we saw at the level of the power spectrum, they get somehow washed out when you perform the integrals. And the most interesting feature here is when you look at the Limbers approximation, you actually see this divergence on small values of L, or large angle separations. And this is something that we already knew from Simon and from other people working on this. But this is the first time that we actually see this effect in a plot. Bottom line, the midpoint and geometric seems to do a very great job. Okay, so let's summarize what we have learned so far. So we have learned that the angular correlation functions are really hard to compute, that Limber is the most widely used approximation, but there is this list of issues regarding accuracy and the validity of the different approximations. And for that, it was clear that we needed to compute the unequal time correlators and at all angular scales. Unfortunately, it seems that the unequal time effective field theory framework does not improve the prediction from standard perturbation theory, and that the midpoint approximation seems to be better on mild nonlinear scales. And what's coming next? Coming next, these two papers. So first the numeric paper where we show you or we provide you with this methodology to compute this angular power spectrum at all angular scales with flexibility to include equal and unequal time correlators. And that's going to be a Python package called Corfu. And then the science paper, where we explain all this story about the unequal time matter power spectrum at one loop. And it's going to be also another Python package publicly available, unequal pi. And we analyze all these approximations and all the validity regimes, and where we conclude that actually the midpoint and the geometric approximation seems to mimic very well the unequal time features. And this unequal time feature seems to be more relevant for galaxy clustering and galaxy-galaxy lensing. So in this case, I think I'm going to stop here before moving to the second part of the talk. And please feel free to ask any questions or any clarification that you'd like me to do. Is there any question?
I don't see any hands up at the moment, so I think you can probably move on to the next section. I'm guessing there will be questions at the end, no doubt.
Perfect. Okay, so in that case, let's move on. Now I'm gonna change topic, but bear with me. Hopefully you enjoy this as much as I do. So this is the SkyPy project. And in this part of the talk, I'm gonna walk you through different things. So I'll tell you about the vision, the structure. I'm gonna tell you who we are, then I'll explain the package and how we are developing this package. And then I explain the two key properties of SkyPy, which is the driver capabilities and the research development. So let's start with the vision. It is well known that observational cosmology and extragalactic observations have been limited by data access. And that's why collaborations have formed around data access, for example, Sloan, Cosmos, or Dark Energy Survey, etc. However, this seems to be changing, and with the upcoming data from LSST, Euclid, WFIRST, it seems that now the limiting step is access to methods, not data. We do have two fantastic emerging methods like forward modeling and machine learning. So in this context, SkyPy is born. So SkyPy is built around methods. And SkyPy is an open source of project, high quality Python package that aims to be AstroPy affiliated with functionality to make end-to-end simulations of the universe and to enable forward modeling and machine learning. And SkyPy is not a replicate of existing code. So in SkyPy, we aim to reuse another AstroPy affiliated packages and another high quality codes that already exist. Okay, let me tell you about the structure. So we have a management structure, we have a board that manages memberships, policies, and we are organized in dynamic teams to minimize permanent SkyPy structure. So we have different stand-up teams, for example, for different specific tasks on short time scales. And once these tasks are complete, the team is down and then we celebrate. Also to say that we expect SkyPy to be rewarded through citations of package and not the papers. And regarding the code structure, SkyPy is driven by a science project. You will hear about that later. And we're organized as a GitHub organization. So we open issues to request or inform of different features, to report bugs, and then that same person or someone else can pick up the issue, work on the code, write unit tests and high quality documentation, and then push the pull request. And then it goes through a code review process by someone from the same team and also from our fantastic infrastructure team. And also we have semantic versioning or staged releases. Currently we have version 0.3 out, that was out last month in October. Right, so who we are. SkyPy is an international collaboration, and we have people from different expertise. For example, here in Manchester, we have Sarah Bridle. She is our chair. We have Richard Rollins, who is one of our coordinators and the main guy in infrastructure. We have Juan Pablo, we have Nicholas and Ian and Laura and myself. And then we have people in Portsmouth, Adam Amara. We have also Philip Sadek and Ginevra Fabole working on galaxies and connecting galaxies to halos. And we have other people like Coleman and also our fantastic gravitational wave team, Ian, Harry, Laura, and the two Andrews. And then we also have people from the other part of the world. We have Brian North, who is our ombudsman at the Fermilab, and then we have Simon, our expert in strong lensing in Stanford University, and people in Taiwan like Keiichi Umetsu and Su Tieng Tam working on clusters. Right, so let me explain the package. As I said, we want to make end-to-end simulations of the universe. So for that, we have features to reproduce everything that you will obtain from your telescope or your CCDs. So things from background to image rendering, going through power spectrum, halos, a huge list of properties for galaxies, gravitational waves, we have supernovae, and just now we have started implementing clusters and Milky Way, and the idea is to reproduce images from different experiments like TESS, POW, DESI, LSST, Euclid, HSC, and of course we need image rendering and spectral rendering. The full list of features you can find on our GitHub page. Right. So how have we been developing this? So the development of SkyPy is being done at different layers of development and also different phases. So we started back in January. We had our kickoff meeting where we set out everything that we wanted to do, how we wanted to do it. And then during the phase 1, we started implementing the intrinsic, like power spectrum, halos, and galaxies. We had our first release in April, and then during the phase 2, we worked on the observables, we worked a lot on the halo features, and started with intrinsic for supernovae, gravitational waves, and clusters. And in that way, we are continuing developing this. Then in July, we released version 0.2, and then entered into phase 3, where we started developing research projects and also continue developing the previous features that were open. And just last October, we released version 0.3, and now we are in phase 4, where we continue developing all these functions, and we start working on the Milky Way and thinking on experiments and galaxy catalogs. Right. And now, okay, so I told you one of the key points of SkyPy is the driver capabilities. So the SkyPy driver is able to run end-to-end pipelines of different functions with loads of dependencies, and it's able to generate outputs in the format of tables, for example. If you go to our GitHub page, you can find different examples already. These 3 examples, and for example, if you go under the examples directory, you find these YAML files. These are config files for the driver. And there you can set up your dictionaries for the cosmology, for the power spectrum that you want to use, and all the different functions that you want to use. For example, you can reproduce this plot, which is a simple example of abundance matching. So how to paint galaxies within halos. And in this case, for example, it's just a very simple model by Vail and Ostraika. And simply is telling you that you might expect your brightest galaxy to be sitting on your most massive halo. And that's all that it is. Right, you can also find another example on galaxy populations from the Herbu et al. Model. And this is the config file. And these are the Dirichlet coefficients that can be used to create SEDs, for example. And the third example is for compact binary merger rates. So gravitational wave merger rates. In this case, we present 3 types of compact binary mergers. And these 3 things it's just examples that you can do already with the SkyPy. And also, this is really exciting. These are the first simulated galaxies using SkyPy and lens astronomy in combination. So it's just some galaxies that are affected by some strong lensing effect. So that's another example of how the user might use SkyPy in combination with other software. So remember, SkyPy is just a tool, and the user will be able to use it the way they please. The second key point of SkyPy is the research development. SkyPy is driven by a science project. How? So if you are a member of a SkyPy, SkyPy is going to help you develop your own research. And once you do your own research, so SkyPy helps you creating new modules or creating new infrastructure. And once you're done with your project, this will feed the public repository, and SkyPy will grow in that way. And currently we have 4 really exciting projects. We have a galaxy forecast by Philip. We have projected ellipticities by Nicolas Tesori, cluster weak lensing by Keiichi Umetsu and Su Tian, and dark sirens with H1 traces by Ian Harrison, and much more to come. But if you're not a member of SkyPy, but you do really want to contribute, you can do it because SkyPy is accepting external contributions. Okay, so coming up, let's summarize. So SkyPy is a legacy project. SkyPy is an open source, high quality Python package driven by science projects that aims to be AstroPy affiliated and does not replicate existing high quality code. And it has functionality to make end-to-end simulations of the universe and to enable forward modeling and machine learning methods. So what's next? So we are going to release our version 0.4 in January next year. And we are currently also applying for funding because, as I said, SkyPy is a legacy project and is not only about science, is not only about a Python package. It is also about committing to equality, diversity, and inclusion. And we do have some fantastic projects along these lines. Okay, so now it's your turn. Open your terminal and you can just try pip install the SkyPy or conda install it or clone our repository and start using it, using import SkyPy. Thank you. Any question?